Okay, so I think we can start now. And okay. Okay. Hey. Hey. All right, so I think today's lecture is gonna be we will see actually the motivation behind the cut matching game, why it is really developed. I talk about cut matching game as if it is a way to construct an expander under adversary, but really the motivation behind that, why we want to construct it that way, is in this lecture. And so we have seen actually two ways. Like if you have a question of whether your graph is an expander, that is, you want to approximate the conductance. Then we have seen actually two ways to answer this, like two very different ways. One is based on eigenvalue, which is to use Shiger inequality. That is, we do the power method, right? And the algorithm guarantee the following, actually. So it either find a cut of conductance at most phi, or say that the graph have conductance at least phi square. So there is some loss in the square in this approximation. And this approximation ratio actually can be very bad, right? It's very good if phi is big, but it can be very bad if phi is very small. Yeah. So, but the running time is quite nice, like at least when phi is quite big, it's near linear. Yeah. Another way to check or approximate conductance is to use latent round relaxation based on LP. And here we get log n approximation. That is, we either find a cut of conductance phi or say that there is no cut of conductance less than phi over log n. So the approximation is log n, but the time is quite slow. Like we just said that it's solved by linear program, but some polynomial time, but slow. And today we're gonna see that, okay, we can get the good approximation algorithm and also fast. And the approximation ratio will be something like log square. And this log square really comes from the number of rounds in the cut matching game. And the time is gonna be, for each round in the cut matching game, we will call one max flow. And the base known bound of max flow is quite fast, right? So this is why this is like both fast and have good approximation. And actually, so we will use this, like we will get this kind of running time and approximation for first the problem of approximating conductance or expansion. But we will see that it is very flexible, this framework. And today I will tell you how to use it to find balanced sparse cut too. Like, it's not just checking if there is any sparse cut. You try to find the one that is balanced. And this is going to be very useful. Yeah. But this framework is going to be like very flexible, and you can use it for many things. Okay, like you will see that it is very, like you can use it to solve many variants of this problem. Okay. And for today, let me assume that your graph is an unweighted graph, and n is the number of vertices, m is the number of edges. Okay. So let's start. So first I will tell you about how to approximate expansion, like from last time, like not conductance, but something related. That is, expansion of a graph is just like you look at all cut, right? And you compare the cut size with the number of nodes inside it, not the volume. That's the difference. Okay. So we will approximate this thing, psi of G. And then I tell you how to adjust the algorithm to make it work for conductance or even for like general D expansion. Okay. Yeah, so this is the goal, right? We are given a graph, given a parameter phi, and we either find a cut of expansion less than phi, or say that there's no cut of expansion less than phi over log n. So that's just the like, if you have this, then you can approximate expansion in log square factor. Okay, so this is like what we will really do is slightly different. So what we will do is that we will show an algorithm that in the first case is just the same, but in the second case, I will actually say that I can find expander x, okay, such that this x have high expansion, and I will embed this x into G. Embed this x into G, and the condition of the embedding is small. Okay. That is, I return x such that x satisfies this. Right? Okay. So why this is a goal? Like why this is useful? Because actually it implies this second case here. Like this thing imply this. And the reason is just simple. By now, like maybe this is quite natural for you to see now. That is, suppose that x if is embeddable into G with this congestion, and let's say that x is an expander. Then what do we have? We want to say that it means that the expansion of G is big too. And well, if x is embeddable is less than G in the flow sense, then x is less than G in the cut sense. Right? So we have that for any cut S in G is at least the cut in X within this factor. But X is an expander, so this thing is at least this. But this together implies that, like here I use that X has high expansion, right? This just implies that for any cut S, the cut size of S in G is at least this much, and you have this factor. Is it clear? Okay. All right, so from now, this is our goal. Either find a sparse cut or embed an expander with small congestion. Right? Once you can do this, either one of this, then you can approximate the expansion. Okay. Now, I will not tell you yet how to do that exactly. I will tell you some things close. That is a subroutine that either find sparse cut or embed a matching. It's not embedding an expander yet, just either sparse cut or embed a matching. Right? Okay. So the subroutine formally is like this. You're given a graph and some cut A and B. Yeah. There's a graph and the cut A and B. let's say A is less than B, and a parameter phi. Then what we would do is, okay, one case is that we will find a sparse cut which is like small expansion. Otherwise, it's very similar to what I just said for expander, but here you return a matching, right? Matching is between A and B, and the matching is of size A. But now you can embed this matching into G with small congestion. Question about this subroutine?
This has nothing to do with A.
Which one that has nothing to do with A, B?
Yes, the cut S.
S, yeah, S have nothing to do, S that doesn't need to have anything to do with A and B. Yeah. It's just some sparse cut. Right. Okay, but now, okay. So that's the problem, sparse cut or embed a matching between A and B. Now, it turns out that this problem is not too hard to solve. And the reason is that let's look at the following ST flow problem, where if you have the graph, the graph G here, then let's say that I add a super source and super sink, and then put an edge from the source to everyone in node in A. And the capacity should be 1. The capacity is 1. Do the same for T. Everyone in B, connect it to T with capacity 1. Okay. And now what is the capacity of the original edge in G? We set it to be 1/phi. So 1/phi here will correspond to this 1/phi here, like the congestion of the embedding. All right. So this is a graph that we will look at. Like it's a ST flow instance. Okay. And the claim is that once you solve this ST flow, like let me call this graph GST. It's just a graph where you add a S and T node. If you solve this ST max flow in this graph, then I claim that you're done. And the reason is that like it's not clear, right? Okay, but we will see why. Okay, like so there will be just two cases. Either the size of the max flow is exactly A, or the size of the max flow is less than A. And why the size of the max flow cannot be more than A?
Because the total inflow is only moderate.
Right, like because this is a cut of size A, right? Yeah. And this is a cut of size B too, but A is less than B. Yeah. Okay. So flow is never more than A. The size of flow is never more than A. So now, let's just see. Suppose that the size of max flow is exactly A. Then, what does it mean? I'm claiming that if this is the case, then you can embed a matching into the graph. So, so let's say that, okay, let's say F is the max flow of value A. And you can assume also that F is the integral flow, like because the graph is unweighted here, I assume that. So you can like each edge have integral value of flow. But once you have that, you can say that, okay, let's look at this F. So this F. Then you can perform, like, you can decompose the flow into path, a collection of paths, right? Any flow, any ST flow is really a collection of ST paths combined together. So, like, For example, you can get this kind of flow, like this kind of ST path. Maybe this one too, and so on. And you know that there must be at least a many path, because that's the number, the size of flow, right? So everyone, like from S here, you will have one path from A and go to T somehow. So actually there are exactly a path that you will get. So is it clear what I mean by doing flow decomposition? Right? Yeah.
Can the path like overlap?
Yeah, the path can overlap because the edge in here have capacity 1/5. So yeah, each original edge in the graph can be used by 1/5 many paths. Right? This thing have 1/5 capacity, but this one have just capacity 1. Right? So you can really think like if you just forget S and T here, it seems like each node in A send 1 unit of flow to some node in B. Yeah, if you just forget this thing. Yeah.
Also the nodes in A are connected with one another.
Say it again.
The nodes inside A, are they connected with one another with the same capacity?
So if there is an edge, original edge between A, then you just set it to be 1/5. Like every original edge have the same capacity. Yeah. Okay. So yeah, so basically every node in A, there is a flow path of value 1, and the endpoint will be some node in B. Yeah. This is what you get from this flow. And now, note that like you can, from this flow path, you can really create a meshing. That is, if this node go and mesh to this node here, then you add one edge, one meshing, like one edge into the meshing, right? Just look at the endpoint of the path, add a corresponding edge into the meshing. Okay. And now, the important thing is that you can see that if I create the meshing in this way, then really the meshing here is just embeddable into G with congestion 1/5. Right? And what is embedding? It's just this flow. Yeah. Okay. By the way, note that I want to know that this flow path decomposition actually can be found in maybe m log n time. If the graph is unweighted or have unit capacity, like you can do some deferred search trick, but yeah, like this can be done fast. Yeah.
We have 1 hour, right?
Oh yeah. I mean. Yeah, maybe this much. I'm not sure. Yeah. Okay. Like if we are doing it in the way which is like straightforward way, you can do it in this time for sure. Yeah. Kind of just do the first search inside of path, inside the flow, and from S until you reach T, and just extract the whole thing as a one path, and so on. Okay. Anyway, now you have that you can get a meshing that is embeddable into G. And this meshing is between the node A and B and has size exactly A. So this is what we want exactly. So that's the first case. You really successfully embed a meshing into the graph. Now what if the max flow value is less than A? So it means that, okay, if the max flow is less than A, then it means that there must be a mean cut of the same value of size strictly less than A. So let's call that mean cut S prime. This is the mean cut in this graph, right? So maybe this, yeah, this is S prime. It might look like this, yeah. Okay. And the cut size is less than A. And then I can define the cut S just to be like, now this is just the same as S prime, but I remove the super source. Just now this is a cut in the graph. Now the claim is that this cut must be a sparse cut. Okay. So before giving this proof in like using some algebra, let me tell you about intuition. Why this should be a sparse cut. And the reason is that, well, you have this set, right? And each node inside A here wants to send some flow to something outside. But because this is a mean cut, it means that this flow here kind of got stuck because there are too few edges crossing this cut. Then this is why it should be sparse cut, right? Like there are like a kind of this many unit of flow, like A intersect S unit of flow that should be sent outside, but it cannot be sent because too few edges. So that's why it should be sparse cut. So now let's do algebra and see that this is really the case. Well, we have that, okay. The cut S prime inside this graph is less than A. Yeah. But what is really the cut size here? Well, what does it consist of? It consists of the original edge here, right? So this is original edge in the graph G. Each of these have 1/5 capacity. And then it also consists of this thing, this edge, and this edge. So this one is just the size of A minus S. So this is S. And this thing is B intersect S. Okay. Now you can compare the two things. And you will get that, okay, move this whole thing to another side. You get that this thing is less than this one. But even if you forget about this thing is less than S. Right? So it means that the cut size crossing S is less than S and times phi. So this is like a phi sparse cut. But you need to actually say that, okay, on the other side, this is less than S bar too, but it's kind of really the same calculation. Okay. So now we get that this thing is less than phi times the size of minimum of both S and S bar. So this is a sparse cut. Question about the proof?
If the max flow is even slightly smaller than size of A, we are counting as sparse.
Exactly. Like.
But that, like, intuition wise, it does not make sense.
Okay. So it makes sense in this because of this. So if the max flow is less than, just slightly less than A, right? It means that at least you know that the mean cut is not is not just a trivial cut. It must be something that maybe like there must be some part which is non-trivial. And now, just now look at this thing inside here. Like the flow inside this part, it cannot go out of this part. So this is a sparse cut here. Yeah, right. So like, I mean, there are other part here where you can send flow, and this is kind of not relevant. The point is that some part that really like a cut that really inside the graph G, the flow inside here, you cannot send it out. Yeah. Yeah. Okay. More question? Right. So now let's reflect a bit. Okay. So we can see that, okay, given the graph, if you choose any cut A and B, you can either find sparse cut and done, or embed a meshing between A and B. Right? But this is not our goal yet. You see, the goal is to embed an expander. We want an expander, not just a meshing. So now, like, we can see that like what we want, we can create a meshing, but we want an expander. But now what is the thing for this, right?
Expander is meaning.
Yeah, like cut matching game is really a tool for you that, okay, if you feed them a bunch of meshing, then it gives you an expander. So this is why cut matching game is for. Is this for? Okay. So now let's try to see how exactly we combine these two things. Like the main ingredient is a cut player algorithm in the cut matching game, and this sparse cut or meshing embedding subroutine that we just seen. And this is like, basically this will be the matching player. Think of this as a matching player, really. Okay, so let me like give you in picture how things are combined and then be a bit more formal again. So what you will have is like, first you have input graph G. This is your input graph. But what you will do in your algorithm is just to create totally different graph, call it X. Yeah. This is your graph, and initially it's just empty graph. Okay. And then you will run the cut player algorithm in X, not in G. Okay. And the cut player only sees X, and he will choose some cut in X. Let's say this one. But this will correspond to the same cut. Like, so X and G have the same set of vertices, but X starts from really empty graph. Okay. And once the cut player chooses one cut, you just look at the same cut in G. And look at this same cut A, B, and G. And let's call this sparse cut or meshing embedding in G. And if you get a sparse cut, you're just done. Nothing else, nothing more to do. But if you get a flow, you get like large flow, then you embed. You can get this flow, but this corresponds to meshing that can be embedded into the graph. Right? So you add this meshing into X. And then the cut player will choose the next cut.
We also have to subtract the flow from the G.
We will not subtract the flow from G. So now, like in each round, we embed new meshing into the graph. Like you find new flow and embed this meshing into the graph. But there are like log n many rounds. So even if you look at all the flow in together, the total congestion of this flow is still quite small.
Cloud square and
Yeah, right. So this is what kind of what going on in picture. So the formal algorithm is here. Like you start with your graph, right? And initialize the empty graph, x0 to be empty graph with the same set of vertices. And there are like log square rounds. And in each round, the cut player reads x from the previous round, choose a cut. What you do next is to call sparse cut or embedded matching. If you find sparse cut, you are done. Otherwise, you find the matching that match between A and B. So this matching can be embeddable into G, right? But what you do, you just add union this matching into your graph X, and you get a new X. And then you repeat, like now the cut player look at the new X, choose a cut, and so on.
So how is it chosen AI BI from xi minus 1?
Why AI BI is from xi minus 1?
Cut player reads xi minus 1 and how do they choose AI BI after that?
So this is from the previous lecture, right? Basically, like there is some algorithm already, like we've seen two algorithms, deterministic and randomized one. He just chose the cut in that way. Okay.
you're just simulating the matching player.
So this sparse cut or matching embedding subroutine simulate the matching player in the cut matching game. But how this guy choose a cut is to really use the algorithm from previous lecture. Yeah. Okay. So we know that, like in this for loop, whenever you find a sparse cut in G, you're done, nothing else to do. But if you don't find any sparse cut, let's say there are like R rounds already, then you know that the cut player, he can guarantee that just after R rounds, the union of this matching XR must be an expander already. This is a guarantee of the cut player, right? Okay. So this is XR must be an expander. But XR will be embeddable into G with this congestion. And the reason is that for like XR is just a union of M1 up to MR, right? But each of these MI is embeddable with this congestion. So the total congestion is just R times 1/5. Okay. So, and you have seen that if you can embed, if you have an expander and you can embed an expander with this congestion, then it means that the graph itself has expansion this much. So now we are done. Question?
The matchings which we are choosing are chosen by cut player in a sense that they are like spreading all over the graph so that it's well connected, right? So
No.
The cut player chooses. Sorry, not the cut player. So the matchings are in such a way that it is finally becoming expanded, right?
So we really don't have any control on the matching. Like we just really find some flow, and that is just some arbitrary matching. You can even think of it as like the worst matching ever. But the cut player, he can guarantee that no matter what the matching is, right? As long as it is a matching of large enough size, it can be bad choice of matching. This union of matching at the end, the cut player guarantee that it's going to be expander.
So now my doubt is, so because this is an expander, I mean it's not like there are not edges are concentrated in one place, like it's all over the place. So, is the log square and or phi congestion can be improved? Is it tight or
Oh, that's a
we are just linearly adding all the conditions? Right?
yeah, that's a good question. I'm not sure. Yeah, I'm not sure.
Because I mean we are now linearly adding each.
Yeah, it's not clear. Like if you can, like instead of linearly adding this thing, can you like cancel flow somehow and get better congestion? Yeah, that's not clear. Yeah. All right. Any more question about the correctness? Okay, now let's look at the time, right? Well, the time, there are two parts. One is the time for the cut player to choose the cut in each round. So we have seen fast randomized algorithm to do that. This is a randomized algorithm by KRV. But actually, I mentioned only that deterministic algorithm can be done in exponential time, and in the homework you will see that you can do it in polynomial time, but you can do it actually, like the best known is now almost linear. So this is basically fast. How about the total time of matching player? Well, it's just this, really like just call this sparse cut or matching embedding, but it's just in each call is just one max flow. Okay. All right, so now we are done, right? We can really approximate the expansion within log square factor. Okay. Now let's see why this like is very easy to adjust and you can solve balanced sparse cut problem. So okay, the thing is like you see, and as Nikhil pointed out, like when the algorithm return a sparse cut, it might actually contain very few vertex inside the cut. Like when we like if the size of the max flow is like very large, very close to A, just slightly less than A, then how the cut, the mean cut looks like is gonna look like this thing, like everything here is like of size almost A already, but must be slightly less than A, so cannot. You have some cut here. Yeah. It can be tiny, like contains very few vertex. And yeah, like usually if you want to find a cut which is sparse for some kind of divide and conquer on graph, like if you want to implement some divide and conquer technique on graph, what you want is really like a balanced one, and this should be sparse too. Okay. So, and this is gonna be very useful, and you see that like, at least it's useful in the cut matching game itself. But there are many more applications of balanced sparse cut. And now, okay, let's see how to like get balanced sparse cut. So now the goal is this. You have a graph and parameter phi for sparsity and beta for balance. Okay. Now the goal is not just to find a cut which is sparse, but it should be as balanced as beta. Otherwise, we're gonna report that for any cut that is much more balanced than beta, like more balanced than beta by, let's say, like log square factor, then this cut which is much more balanced cannot be too sparse. Okay. So it either find about cut, which is like, think of it as you want to check if there is any sparse cut sparser than phi, which is as balanced as beta, but there are some gap in this guarantee in both sparsity and the balancedness. Yeah. Yeah. So instead of saying that there is no such cut, it just said that there is no cut, which is much more balanced than beta and much sparser than phi. And by much here, it's just not too much. It's just like log square factor away. Okay. And this is going to be quite useful because you can see like once you have this subroutine, you can do some kind of binary search. Like you can say that you fix phi and you can binary search for the biggest beta. So you can find like say the cut which is most like the cut which is phi sparse, but most balanced as much as possible. Or you can say that okay, you want to find the cut which is beta balanced or approximately beta balanced, and among that it should be as sparse as possible, something like that. Okay. All right, but this is our goal. And as before, what we will really do, like in the first case, we'll get sparse cut, the same. But in the second case, instead of report that there is no cut, what we would do is just like, we will return some certificate that it must be this case. And what is that certificate? It's gonna be this. What you will return is, we'll return something called, that I just call almost expander, X prime. And together with a set of fake edges F. Okay. And what do I mean by this too? First, if you union X prime together with F with these fake edges, now you get an expander. Like X prime itself is not an expander. Like, but if you union it with these fake edges, it is an expander. But what you embed into the graph is just X prime. Like you don't really embed the whole expander. You embed some subgraph of an expander. And F here should be small, not too big. Okay. So yeah, I call F fake because we don't really embed F into G. Like only X prime is embedded. And X prime is almost expander because like it is an expander only if you add F into it. Okay. And why this goal? Well, because given this above X prime and F, then we can conclude what we want. We can conclude that there cannot be any cut that is very much balanced than beta and much sparser than phi. This is what we're gonna say. All right, and here's the proof. Okay, let's see. So this step is going to be very similar to before. So because we can embed X prime with this into G, then you get like X prime is less than G in the cut sense. So now you just compare that, okay, look at any cut, like the cut size in G is at least a cut size in X prime with this factor. Now, actually, I'm gonna say that this cut size in X prime is as big as the cut in X, actually. I will prove this soon, but the idea is that here we will exploit the fact that S is kind of balanced. Like if S is balanced enough, then the cut size in X and X prime is kind of the same. But okay, if this is true, then we are done, right? Because suppose that this is true, then, well, X is an expander, so you have this. Okay. So why is it the case that the cut size in X prime is, although X prime is subgraph of X, is also, this cut is still as big as the cut in X. Okay. So let's draw something maybe here. So this is X, maybe X prime, but there are like some fake edges lying around, and the size, the number of fake edges is just here, beta R. Okay, and now if you say that X, let's say that no, yeah. X is if S is a cut which is balanced, then okay, if you look at the cut in X, like, so there are, so in X there are like both real edges and fake edges, but this thing together is big, because X itself, after you union with the fake one, you get an expander, right? So this thing is big, and how big? It must be this big, because you define S to be big enough. Okay, but if this is big enough, then no matter what, like, you must say that like the fake edges cannot be everything here, because it's just like this is much bigger than the total number of fake edges. Okay. So I say that like if you look at this cut S, more than half of the edges actually must be real edges. So F is just smaller than half of the cut size. Okay. So once you have this, then we are done. Like, look at this cut, not S prime. Look at this cut in X prime. It contains real edge and fake edges, but more than half of it are real. So you get this. So you see, this is only true for the balanced enough cut S, right?
So we are telling the whole F set is less than or equal to beta, right?
Yeah.
But it might not actually that some edges need not cut the.
Yeah, like F. Yeah, we are very crude here. Yeah, there can be F here and here, but like we say that even if the whole F is really along this cut, then it still doesn't matter. Okay.
If we have that solid,
Say it again.
first if we have that solid, everything assumption of
I don't hear you well, sorry.
Where is the 1000 factor coming from?
Oh, 1000 factor. Oh yeah, here. So yeah, let's say that. I just choose some constant. Yeah, but. Okay. So because there are few fake edges, If S is big enough, then it's gonna be still expanding. All right. So now you can see that for any cut which is balanced enough, the expansion in the graph must be quite big too. If you can really embed this, if you successfully embed almost expander with few number of fake edges into the graph. Okay. And now, now the approach is like once we have this goal, the approach is going to be super similar to what we have seen. Well, we can just define this subroutine for balance cut, where we say that we either get balanced sparse cut or we can embed meshing with some fake edges. So the setting is very similar. You have a graph, you have a cut, the same. What is different here is just you have balance parameter. And what we're gonna do is that, okay, first case is we get a cut, which is sparse and but balanced. Now the other case is you will get a meshing M prime together with fake edges F, such that if you look at M prime union F, now it's going to be the meshing that we want just like before. Like it's the meshing between A and B of size A. But M prime by itself might not have size A, right? But F gonna have, like, there are some fake edges here, but the number of fake edges is just at most beta. And you can embed M prime, into the graph. Okay. And so it turns out that, well, if you look at just the same graph that we have defined before, and look at the size of the max flow, F, okay. It turns out that the algorithm is exactly the same, except that you change the threshold. The threshold used to be just exactly A. Now you say that, okay, as long as the cut, like, as long as the number of the size of the meshing, like the size of flow is at least A minus beta, well, then it means that, okay, for most of these nodes in A, so more than A minus beta, you can send some flow to B, right? So this will correspond to the M prime. And there will be some fake edges, like there are like, the rest here is beta nodes that you cannot mesh. You just say, okay, add arbitrary meshing from this guy to some free node on the B side. This is gonna be your F. Sorry, I use the same F here, but so this is, let's say this is the V for value. Yeah. This is gonna be the fake edges, right? So you can see that, okay, you have M prime of size A minus beta. You can embed M prime into G, and F is small. Yeah. So this case is clear that you get the meshing like this. And now, if instead we have that the value of the cut is less than A minus beta, now we're gonna use the same proof or similar proof to say that you will get a sparse. First, you know that you get a sparse cut, but now it's not just some sparse cut. The sparse cut is gonna be as big as beta, like beta balance. Can you tell me like why it should be balanced at least, like intuitively? So
Because these fake edges are always cut, and that is why beta width always stays.
So let's see. Yeah, that's I think that's right. Like, okay, so basically you have that this guy can send flow successfully, but there are a bunch of other guy, at least beta here, that cannot send flow. And basically the cut, like this is the guy that cannot send flow, so it should be on the side of the mean, like on the same, like on the side of the mean cut. Basically they cannot send flow, so the fact that they cannot send flow means that they like their flow kind of get stuck in the mean cut, which is why all of this is on your cut size. So that's why your cut is balanced. So to make this precise, well, you just need to like do some like inequality match, just write some inequality and make sure that this is the case. Okay.
So all this we are doing only to get the cut which is balanced instead of just any sparse.
Yeah, right.
But we are also losing some factors on the way.
So we lose the fact that we cannot just say that, okay, we cannot just say that, okay, so here is good, it's better, you get sparse cut, which is also balanced. But the other guarantee, like, the other case is become quite weaker because it doesn't say that, okay, no balance, no sparse cut at all. Just say that, okay,
No,
just
more balanced, much sparse.
Yeah, exactly. Okay, good. And I will let you do this as an exercise. Like, given this like subroutine, how do you combine it with a cut matching game to solve the goal? But it really just follow the same approach. Okay. So now we are done for 2 problems, okay? And now I'm gonna like talk a bit about the issue that we assume, like that we kind of ignore before. We kind of say that the graph the graph G itself is unweighted, okay, has unit capacity. But what if we want to approximate the expansion in general graph? What would go wrong in what we discussed, yeah? And how we want to fix it? Well, first of all, the expansion in capacitor graph is just the same thing, except that instead of this, you use total capacity of the cut size instead, right? Okay. So, like this is just technical problem, like technical issue, not it's not conceptual, conceptually not that important, but like if you want to implement it fast, we need to take care of it. So there are 2 problems. So the first problem is about flow path decomposition. So like recall that if once we have computed the flow in this balance sparse cut or matching embedding, then we do this flow path decomposition we said. But like to like extract this flow path into the matching, right? But this is not very fast, like not really fast in capacitated graph, because it might take mn time if you want to extract all the path explicitly. And the reason of that is not just about implementation, but it's really about some combinatorial property of flow in capacitated graph. Because actually the total length of path can be as big as mn. Just to represent, like to output this thing, just already take mn time. So why is that? Let's look at this graph, for example, right? So this is like, let's say the capacity, the length here is n, and the capacity of each edge here is n too. The capacity of this edge is 1. Okay. So, and there are like n nodes here. Okay. Well, now you can see that there will be n many paths in the Mac flow. Right. But there are n paths. Each of the paths have length n. So just the total length of the flow is n squared. Although the total size of the graph here is just O of n. You see, right? Like this is just it's a big problem for running time. Like in general, there can be as many as m paths, and the edge length can be like long, like n. The path length can have length n. So this is so-called like flow decomposition barrier. So okay, do you like see why this is not really a real problem for us, actually?
So like we only need the start point and the end point of the
Exactly. Like we don't need to output the path explicitly. What we really want is just a matching, which means that it's just an endpoint of each path. Right. And yeah, I will not have time to like tell you why, but using some link cut tree data structure, like there is some data structure that allows you to extract the endpoint of path in time which is quick. So a very quick sketch of this thing, because I will not talk much about data structure in this course. But so if you have S and T, yeah, and if you want to like to extract just one endpoint, well, you can like do some. You traverse along the flow, and this now can have maybe like capacity which is different, 3, 2, 11, something. Yeah. Then there is like a data structure that allows you to like subtract the whole flow value of this path by 2. Like look at the minimum guy in this whole thing and subtract the whole thing by 2. And they do this implicitly using some data structure, and this implicit operation just take log n time. So once you find this thing, you look at the 2 endpoint here, This is your endpoint of your path. Subtract the whole thing by 2 and repeat something like that. But like you get each endpoint of a path in log n time per path. Anyway, let's say that this can be done. Yeah. From here, what we will get is like a fractional meshing. Such that, so basically for each endpoint, so why do I say that this is a fractional meshing? Because, so even though in the graph here, each of these have capacity 1, everything here has capacity 1. Now, the way that I define the capacity here, this one now, like you will put like 1/5 times its own capacity, and this is can be less than 1, right? Can be strictly less than 1. Yeah. So the flow is not integral anymore. Yeah. But like once you extract all the endpoint of the path, you will get a fractional meshing. But there will be like only m non-zero weighted edge in this fractional meshing. And the reason is that, so the reason is that, yeah, why is that actually?
Because total edges in the graph are becoming 0, so some of them are removed.
Right, exactly. So yeah, if you do flow path decomposition in any flow, in any graph, you can say that there can be at most m many paths. And the reason is like, yeah, when you do flow path decomposition, you can assume that you extract the whole path by large enough so that at least one edge in a graph have flow value become 0. The flow value on one edge in this path have flow become 0. So for one path, you remove one flow completely from one edge. So that's why there can be at most m path. Okay. So before, like there can be n edges in the integral meshing. Now it's gonna be m non-zero weighted edges in the meshing.
Is it mod A edges or N edges?
Sorry?
It's mod A edges, right?
Mod A. Oh. No. Yeah. It used to be A edges. Yeah. Right. Yeah. Still correct. It's at most.
Oh.
Anyway.
No,
Yeah. So, but like in this fractional meshing, the size of m, the fractional size is still A. Yeah. By fractional size, I mean the total weight is still A. Okay. So anyway, we can extract this fractional meshing fast. Yeah. Without getting the whole flow path decomposition. And now, but this leads us to the problem 2. That is, in the cut meshing game that we talked about, we like most of the time we really just talk about in each round you get a integral meshing. Okay. But here we get a fractional meshing. So like in each round we get a fractional meshing instead of integral one. But yeah, like I kind of hand wave in exercise session that this is really like nothing really changed. Like the cut player when they now the graph that the cut player see is not the integral, it's not unweighted graph, it's become weighted graph, but he just need to find a balanced sparse cut in that weighted graph, and the same algorithm for the cut player is this just work. But the total running time of the cut player is now O of m instead of O of n. And this is O of m because the number of edges in the meshing is OM. So this time is the time for, let's say, the randomized cut player algorithm. It takes time linear in the graph size. So the graph size now this much. Yeah. Anyway, this is how you handle a weighted graph. There's just some technical issue you need to handle, but it's not too hard. Nothing conceptually new. Okay. And now let's see, at least it's just, again, kind of seamlessly generalizable to something more general. Let's say you want the expansion. Do you recall the expansion? Yeah, so, right, this thing is the cut size, right, over ds where d is just general thing, and the expansion is general, more general than conductance, right? So what if we want to approximate the expansion? Well, can just define, we just need to adjust them. There are two main ingredients. We just adjust both of them accordingly. The first ingredient is this sparse cut or meshing embedding subroutine. The second ingredient is an algorithm for the cut player. And well, how will we adjust it? We can just the first one we will adjust it in this way. You give a graph again, you give a cut such that the A side is smaller in D than the B side. Now you get a parameter phi. And now what you return is you either return a sparse cut or you return something that I call demeshing. What I mean is that, well, you get a cut on A side and B side, and then each of these guys have some demand. This is demand dA and this is demand dB. And then, well, you will get a meshing where each of these nodes can mesh to dA many nodes. And the guy on the right here can mesh to dB many nodes. Yeah. Yeah. So can you tell me what would be your guess on how to solve this subroutine?
Just multiply edges, put more edges with single capacitors.
So
We will complete by quadratic graph and we equally distribute the weights.
You just need to change the ST weights.
D of your.
So yeah, so basically it's what Aditya said, and I think Nikhil. So basically instead of saying that each node here, you set it to be 1, well, you just look at node A, and this is like you get dA capacity. And also here, you get dB capacity, right? And well, you see that like if you get the flow case, then each of these guys like they will have dA many flow going out of it. And if you get a like if the cut size is less than like the dA, well, you can prove in a similar way that you get sparse cut in this sense. Yeah. This you need to work it out. Yeah, this is an exercise. Yeah.
There's no restriction that D needs to be integer. Right?
No.
D can be
Anything. Yeah.
Then again.
And okay, yeah, I forget to say that. What should be the capacity here on the original graph? Say it again. C/5. Yeah. So if the capacity used to be CE, then you just set it to be CE/5. And the reason is that, yeah, we want a mesh like this flow to have congestion 1/5, right? Okay. So like all of this, I think it should look kind of intuitive to you, but why exactly it really, like why this algorithm really works precisely, I encourage you to work it out. Okay. Okay.
If DOA is not integer, how can we do the multiple path decomposition?
Well, we will use this like this, like you just extract like the endpoint of the path, like
Using
like
data structure.
yeah, like using data structure. Yeah. Yeah, the number of paths is still gonna be like at most m plus n, something like that. Yeah.
Yes.
Yeah. Okay. So this is like how you would adjust the first ingredient. How about the second ingredient? Well, like you just need to set that the cut matching game should work for the like when the graph, like when in each round you get, instead of matching, you get a D matching. This is what you need to work with. Yeah. And again, in our discussion session last time, like I kind of mentioned that if we want, like if in each round the matching player, instead of give the matching only, it gives D matching, then at the end what you get is something like an expander with degree profile close to D, within like log square factor maybe. Okay, but actually this is like, there's some question actually that I want to ask. So this is a question. The question is that, can we make what I kind of hand wave in the discussion session formal? To be precise, let's say that we are given degree profile D, and let's say that it is an integer, because we can scale things up to make it integer. So I want to ask you to show how to construct an expander with n nodes, such that each node have degree at the end close to D with a log square factor, using the cut matching game. When the matching player return bipartite D matching in each round. Okay. So what I want is that the number of rounds should be log square, and the running time of the cut place should be poly n or even near linear in the size of the graph. But it's important that I think like what I want here is that these two numbers should be independent from D. Like dv can be like any number like which is independent from n. It can be arbitrarily larger than n. But the number of rounds should still be like depending on n, the size of the graph. Not like this guarantee should be like depends on the size of the graph, not the weight, basically. Yeah. So this should really be true, but it turns out that this is not in the literature. Yeah, it would be useful if someone write a note and publish, so that people can cite. So note that there is a cheating approach where we just run the cut machine game on graph with dv nodes. Like, if you know what I mean, like if you say that this dA is 10, then what you run is like you just split this thing into 10 nodes actually, and then just run the cut machine game in this split graph, and then just contract thing at the end. So this will work, right? This will give you the expander with degree profile that you want, but you can see that the number of rounds and the running time now will depend on D. So this is why we don't want this cheating approach.